Okay, we're going to solve this problem from the book, Chapter 2, Number 21, algebraically and then graphically, so two different methods for the solution. Okay, we know that the car accelerates from one speed to another in 6 seconds, and we want to know what its acceleration was and how far it traveled, assuming constant acceleration. So if I draw a v versus t graph, it starts at 13 meters per second, which is vi, which is the important part. The number doesn't really matter at this point. And it ends with a vf of 25 meters per second, and that took a delta t that we know of 6 seconds. So if we're going to find the acceleration, what we're trying to find is the slope of this line. And so the slope of that line is going to be the rise, which is delta v, vf minus vi, over the run, delta t. So that's going to be 25 meters per second minus 13 meters per second over 6 seconds, which will give us 2 meters per second per second. Okay, the next thing we want to know is how far it traveled, and that means area. So we want this area here. So that area, it's a trapezoid, it's 1/2 times this length, which is vi, plus this length, which is vf, times this, which is delta t. That's just your trapezoid area rule, which will be 1/2 times 13 meters per second plus 25 meters per second times the 6 seconds it took, which will be 114 meters. Okay, algebraically, we want to start with a diagram. So the vi is 13 meters per second. The vf is bigger, 25 meters per second. This took place over an unknown delta x. The delta t is 6 seconds. Positive is to the right. The acceleration, I know, is to the right because we're speeding up and our velocity is positive, so the acceleration and the velocity are in the same direction. Okay, if we want to know the acceleration here, we can just use the definition of acceleration, which again will be the same thing we had above. And once we know that acceleration, we developed this model in the lab. And we know all of these numbers, and if we plug all this in, we get the same thing we did there.